This presentation is titled Quantile Regression Workflows. It is for the conference PyData Global 2024. My name is Anton Antonov and I'm an applied mathematician. I also brand myself as a senior data scientist or senior research scientist. So this presentation is targeting data scientists wannabes, data analysts, people who work with time series and statistical models part-time or full-time. So I'm going to be showing different examples of rapid specification and execution of quantile regression workflows. We're going to discuss fitting, outlier detection, conditional, cumulative distribution functions, simulations, and I'm going to be using a few types of time series data. So I like to introduce quantile regression with this cartoon. It is a modified version of XKCD cartoon. And you can pick your favorite method somewhere here if it is not quantile regression to the left, and so quantile regression, claims to be superior to all of this. So here actually, maybe this is another example, more to the point. This is the first example, so you can see this purple curve. It's fitted at probability 90%. And the red one at probability 10%, and the median or 50% probability, it's green. The median corresponds to the mean. Now I'm going to compare the mean and the median later on. So this workflow's flowchart encompasses the workflows we consider. I'm going to zoom out, and so as typically in data science or statistics, we take the data, we transform it, clean it, rescale it, modify it in some way, standardize it. If the assumptions of the data hold, we start doing the regression fit, and if we have acceptable fits, we pursue the ultimate outcomes of our analysis. If we have done too many fits and we didn't get an acceptable fit, well, we can give up. All right, so before going further, I would like to say that I have these three panels here. To the left is a panel with a mind map, which is going to keep us oriented about the presentation, and we're basically somewhere here. And the second, or the middle panel is with the presentation itself. This is Visual Studio Code, and I'm running a Jupyter notebook here. And the third panel to the right is with some other materials I'm going to be showing. This package, Python package Regressionizer, is the one I'm featuring in this presentation. All right, so I think I need to zoom in for the next slide. So a little history. So quantile regression was attempted, or more or less successfully applied mid-18th century for astronomy-related problems. Approximately 50 years after that, people tried to, Legendre and Gauss, they tried to apply linear regression also to astronomy problems, and not just tried, successfully did so. So 50 years ago, Roger Kionka and collaborators introduced the modern computational framework for quantile regression. They also worked out the inference part. So, coming from statistical background, discussing inference for quantile regression for statisticians is important. So, the computational framework is optimization based. It's not ad hoc. It's not some sort of poor man's kind of method, in which the points are being counted, discovered in some way, some averages are being made ad hoc. No, it's a computational framework based on optimization, and with very sound theoretical background. So Roger Kionka, he was a professor in University of Illinois, Urbana-Champaign. I worked for Wolfram Research. Its headquarters are also in Urbana-Champaign. So I met Roger Kionka, I think 10 years ago. He was a professor both in economics and statistics at University of Illinois, Urbana-Champaign. I think right now he's in the London University in England. So Roger Kionka wrote this package QuantReg, again, soon with collaborators. I have made some enhancements in R, but I also implemented quite a lot of Wolfram language, also known as Mathematica packages or packlets, and so you can find different packages, say, in the Packlet repository. So I have done also a cycle of lectures for on quantile regression for Wolfram U. So you can find some of these lectures here. They're different. I think they're altogether 5 live coding sessions with quantile regression, but that's with Mathematica. So this presentation is with is made in Python with the package regressionizer. So before going further, I tend to forget discussing or listing quickly what are the good features or great features about quantile regression, especially compared to some other approaches. So first of all, quantile regression is robust when it comes to outliers. This is again when I was mentioning mean and median. It is how median is robust one-dimensional estimate compared to the mean. So similarly with quantile regression, we have similar kind of effect. So we can do conditional cumulative distributions. This is one of the biggest, the first one, robust with respect to outliers. It's one of the biggest features, but I personally, I don't find it that important. Or it is there, right? So I use it, but I'm much more interested in the rest of the features, and especially the conditional reconstruction of the distributions. That's actually quite interesting. It is for analysis, but also for simulations. I like doing or dealing with operations research problems, for manufacturing, for industry. And so from my perspective, being able to simulate or being able to analyze the signals in order to do simulations of the process is very important. We have variance estimates more or less by default using quantile regression. There are some relaxed assumptions about the signal variance, meaning the signal can be heteroscedastic. We can actually see it here. So in this, here you can see how the variance is not constant. But with linear regression, some kind of constant variance is assumed, in the theorems which are proved. So quantile regression, there is no such assumption. So back to the list here. Yeah, with star I have put, mentioned my favorite properties or features of quantile regression. So contextual outliers and detecting anomalies. With quantile regression, this can be done in a very interesting way and in a very straightforward way too. There are other ways to find outliers and anomalies. I'm not saying quantile regression gives all of them, but it definitely introduces a very interesting set of algorithms for detecting outliers and anomalies. All right, so the package here, I'm not going to go through this list, but the idea of this package is that compared to other packages I have seen or people have reviewed for me, Python packages for doing quantile regression, is that it's very easy to make quantile regression, to specify quantile regression workflows. One of the ways to prove this, I'm trying to prove it here. You can see I have this natural language command, right? So we're basically creating a pipeline. This is natural language specifications. The pipeline here is being created from these natural language specifications. The reason I'm listing this is that it is very easy from this more or less informal specification to actually produce this pipeline. There's almost one-to-one correspondence, and you can see it's pretty close to what we see here. So this is some sort of an indirect proof that having the ability to very quickly specify quantile regression workflows, it's just invaluable. I'm returning to this example too much. Maybe I should have expanded it here, but you can see this pipeline here. It's very simple. I'm taking the data, I'm doing quantile regression with 8 knots, and I have listed the probabilities, which we also see here, and I'm just plotting it, and basically this is it. This is actually a very quick and rapid way to get your signal plotted with the fittings being shown. I don't know any other package in Python which does this so economically and so quickly. All right, so this was too much of advertising, I assume. So before going further, let me actually go to the mind map and basically say, look, we passed this first part. this is probably the heaviest part about the fitting examples. And so the first one, I mean, I have shown here some list of ad hoc functions I'm doing, but let's actually use these Chebyshev polynomials, and I'm using certain probabilities like 10, 50, and 90%. This pipeline here, actually also the regressionizer package also can use least squares fit. Let me plot it. So we can see here how the probabilities I've mentioned, 10%, 50, and 90, have been shown, but also the mean, which is the least squares fit, has been shown here in orange, right? So, and it almost coincides with the median, right? Now, as I said, there's a direct analogy with the one-dimensional case. The mean, it's a less robust estimator compared to the median in one-dimensional. Also, in if we do quantile regression over these two-dimensional signals. So let me do some other example here. This here is being used to prove that the quantile regression worked. So I have counted the points below the red curve, and we see here they're approximately 10%, also below the green curve, and they're approximately 50%, and below the 90%, which is again approximately 90%. When I say count, people think that I'm doing some counting, like I'm kind of circling or taking some kind of subset of these points, and I'm finding the quantiles in these points here, just on the y coordinates. No. This here, it's with a basis. There's a certain basis of functions. In this particular case, the same basis is used for both quantile regression and for least squares fit, and that basis it's a system here. It's a system of Chebyshev polynomials. So basically, I ad hoc derived them here. I could have used another set of polynomials. This basis is a very certain optimizational method which is being used to find the weights for this the basis of these functions and produce these curves. I think this would be probably the only theory I'm going to mention. So let's actually do this with B-splines. We get more or less the same results, the same kind of output. But here, instead of specifying the Chebyshev polynomials or whatever polynomials, I'm actually saying, if I say quantile regression without underscore fit like above, if I say quantile regression, this by default uses a B-spline basis. And I just can specify different elements of the basis. What are the number of knots, or what is the interpolation order? So here I prefer working with the actual functions which correspond to the quantiles. So if you say take regression quantiles, we are going to get a dictionary of the probabilities, the probabilities being as keys, and the corresponding functions to these curves here being shown. Definition here, regression quantiles, this is the definition how we're going to refer to these curves, right? So this notation or phrase introduced by Roger Kionka collaborators. So again, one of the big things about, so I have this data, right, which I was showing earlier. So imagine I have changed some of this data. I have introduced a few outliers. Let's actually see what kind of fit we're going to get. And this is the illustration of the quantile regression being robust when it comes to outliers. You can see, because I put at the end of this data, it's approximately, I think, 600 points. Let me see. Yeah. So you can see that at the end of the data, I introduced these outliers. So if you look at the summary of the data here, I'm not sure why it's so misaligned, but if you look at the summary here, it's basically, they're all kind of relatively small on the one, between 0 and 1, well, between -1 and 1. Now I have introduced these outliers for 2 of the points. Then I make the fitting, and you can see the quantile regression is almost unbiased. Maybe the 90% is somewhat a little bit biased, but not so much, I would say. Definitely the least squares has changed a lot. And so this is the robustness, this illustrates the robustness of quantile regression when it comes to outliers. All right, so I'm going to be using here temperature data, and I'm going to make the fit and make the plot. So one minor detail here. or major, depends how you look at it. I haven't figured out how in the Jupyter notebooks, when I put the plotting, the actual plotting, how to output it here, in the cells. In a sense, I have to do this this cell separately. I need to specify the plot. So you can see the plot is already computed. Right now, what I'm doing here, I'm taking from this object the last value which it has in its pipeline, and I'm showing it here. And so here, what we see is quantile regression for temperature data. I think this is Atlanta, Georgia. You can see I have, I usually, like taking the summary, and what I was saying here, if we look into this workflow chart, yeah, we have taken the data, we probably compute summaries, we might rescale. I'm not sure, do I have examples with rescale here? And then we do the fitting. So basically, here also we might be looking, say, for outliers, right? So this is where we are, right? In this plot, I have put this regression quantiles at, let me zoom out a little bit. I have put them at 2% and 98%, and I'm basically saying everything above and below them is an outlier. Now you can see that, so this point here is an outlier, absolutely speaking. So, so if I just project all of the points to the y, I'm going to get, this is going to be an outlier. But some of these points here, they're contextual outliers. They're basically, and also this is another absolute one. But some of these points here, they're contextual outliers. Now, my definition for outlier in this particular case is just being outside of these curves, right? Like 2% and 98%. But you can change it depending of how you do the fit with how many nodes, and like say, actually, I think this is slightly overfitted. Let me try it with less number of nodes, see what is happening. Yeah, maybe the fit is somewhat better. All right, so again, I'm kind of counting the points here, trying to prove that I get very good correspondence between the number of points below and above. I insist on this example here because this is one of the ways for me to test the regression, the quantile regression algorithms. Like if I change something in the code, I would expect this to be holding, to a large degree with a relatively large precision. All right, so one of the things to do is that after you have made the fit, you might be interested in the error plots, and so here what is going to be showing, right, somewhat slow. So basically, I want to see they're not necessarily errors, I call them errors, but they're residuals of the fit, and they might be used to do outlier detection. So let's talk about outlier detection again. So you can see here, if I have made my regression pipeline, which is very simple here. Regressionizer, I'm creating the new object, regressionizer with this temperature data. I have fit my my regression quantiles at probabilities 1% and 99% using interpolation order 3. This is for the B-spline basis. And then I say outliers. So these are the outliers, and they're listed here as a dictionary in which bottom outliers and top outliers. Hopefully I'm actually showing them here, right? Yeah, so you can see here that these are, my top outliers in green. They probably should have been in red because it's hot, right? Now this is temperature in Celsius degrees, so you can see the bottom outliers were also given here. So one way to get the outliers very conveniently is in this way, right? So the pipeline, there's always a pipeline value, so to speak, and if you say fit regression, do just quantile regression, the take value is going to be regression quantiles. It's going to be a dictionary of functions. But if I have a plot, or if I have like this command outliers, then the pipeline value, right, with take value, what I'm going to get is this dictionary of outliers. All right, so moving on. So where we are actually, so we're still discussing outliers, and I think I need to mention, I think I'm having too much outlier discussion here. All right, so there's some sort of, we can call them point anomalies. So if I fit this curve, and let me actually show this here. So imagine I actually have fitted this, let me see, maybe with 20, let's see what is going to happen. So you see, this actually fits, this red curve kind of goes through the points. And I think the interpolation order is maybe a little bit more than I expect. Let me actually make it even less, somewhat smoother, right? Now, how satisfied I am with this fit? I might not be, right? I think it's underfitted, right? From another perspective, maybe it's actually good enough fit. I might consider it like that. And I have specified here for some reason 0.2%. Let me actually do 0.5. So here, right, I mean, I get somewhat more, central following here. All right. Now, if I put more nodes, right, like say, if I say that I want to have more nodes here, then I'm following this curve closer. Now, if I go back to this less smooth representation, right? Smoother representation, less fitted. I might say, if I look at the residuals with this between this curve and these points, the ones which are too far away, they might be my point outliers or point detected outliers, and this is what is happening here. It's basically I'm using this fit and I'm finding these outliers. If I do this, I can also do this in a somewhat different way. So instead of looking at the point outliers by using a certain outlier detection algorithm, right? Like this quartile identifier parameters. It's like well-known one-dimensional outlier detector. So I can find them in this way, but I also can do it using a different outlier identifier, or I can do it also by threshold, for example, and using relative errors or absolute errors. I'm going to demonstrate this later. This is much easier and better to be demonstrated using interactive interfaces. All right, so, and yeah, this financial data, I think this is General Electric stock options or something like that from. Oh, these dates here are wrong. Hopefully I have, the dates here are wrong because they have been calculated with a different epoch. But again, when I use this data in the interactive interfaces, they're with the correct dates, correct years. All right, moving on. An interesting use case is when you have a certain pipeline, certain data time series, and you have fitted some curve through it, you might want to get the points which are close to that fit for whatever reasons. This is one way to pick outliers, or another way to remove outliers. So it has happened in many at least a dozen of situations. I had to use that, but basically this is some sort of representative time series, based on this regression curve, regression quantile, right? And I have put it here through, say, certain probability, like which I have used, at 3%, but of course, it can be somewhere else. And so, anyway, this here is just a convenient feature of this implementation of the regressionizer package. So this is one of the favorite topics I have. Let me actually show what it is here. This might, so with quantile regression, we can fit all of these curves at different probabilities. So you can see here, this is more or less, like 11 different probabilities. And now if I pick a certain line, like say this one here, I can actually reconstruct the distribution. So you can see this conditional distribution. The distribution is not obviously there is no assumption that the variance is constant. It can be actually not just not constant, but it can be very skewed or differently skewed at different points. And you can see what, say, because this is temperature, right, in a southern state. I think this is still Atlanta, right? So in the summer the temperatures are more clustered, right, and in the winter there is a larger variance. So again, I can reconstruct the cumulative distribution function at any of these regressor points, right? In this particular case is time. So let me actually do here, show how these functions look like. So you can see this is the the cumulative distribution function. All right. So somewhere here, I think this is an example that we can do this for multiple time points. We can do this reconstruction. All right, so going back here, we're going to be talking, so we passed the pointwise and contextual outliers and the CDF reconstruction. This is more like a third wave applications, which I'm talking about simulations, and then I'm going to be talking about the interactive interfaces. And it's probably easier to experiment with regression, not just quantile regression, with regression if you have interactive interfaces. All right. As I said, I'm very interested in simulations. I'm very interested in operations research, and very often when I have some kind of device or factory, right, the different inputs to it can be shown as time series. Think about, say, the AC of a certain building, right? So we have the temperature of the outside and the number and the electricity, you know, which is being used to cool off or heat up the building. So these are different time series. But if I make some kind of operations research or optimization problems, if I solve them, I don't want to use the time series I already have observed. I want to use different time series, and this is what this is about. This is about using time series which are generated, and they look quite a lot like the original ones. And so this is what this is again. Regression either provides this. It can, after you have done the regression, you can say simulate, you know, how many points you want to simulate, and then you're going to get you get the corresponding time series. All right, so we're here in the interactive examples. Let me actually show this here. So I didn't have time to implement all of these features. So what is happening here? Just a moment. Hopefully, I'm going to show that. All right. So first of all, yeah, we saw the distribution data, and this is not a time data axis. It's just points right here. Let me zoom out. I think I'm zooming out, maybe. All right. So if I choose the financial data, we get this. But if I say that this is a data axis, as I promised, this is going to be with correct dates right here. And you can see with this, if I use 10 number of nodes, we have we have this kind of fit, right? But I might actually go further, right? And so I can have a very close fit now. And again, maybe I should have chosen different coloring here. I would like to mention a couple of things. So I actually did mention here that I want to make analogies with neural networks. And so there's a direct analogy actually. So in neural networks, we have this nonlinear, we have superposition of nonlinear basis functions, right? And so similarly here, it's a linear basis, but they're still not necessarily linear. We're using B-splines or Chebyshev polynomials or whatever, right? And so we use these functions, and we have an optimization method which actually finds the weights in which these functions have been combined into one big function. And so we can overtrain relatively easily, and maybe let me use the temperature here as an example. So this is actually overtrained, right? So you can see how if I use a smaller number of nodes, I'm getting basically much smaller number of nodes. This seems to be a better fit signal, right? And let me actually put some other probabilities here, and just to kind of show this better, right? The curves better. So we can see this orange curve, right? It's for example, right, which corresponds to the median, to probability 50%. And so we can see it follows fairly well what the signal does. Now, if I put more points here, this is going to be overfitted, right? So actually, the median, it's not even being shown, right? So basically, in neural networks, very often they're like black box. We want to overfit them in order to understand their boundaries. With quantile regression, obviously, at least in 2 dimensions, we can visualize what's going on. But it's a very good idea to try to overfit your quantile regression model in order to figure out what exactly you are doing, how many nodes you should be doing, and what kind of interpolation order So this can be automated. I haven't done this in Python, but I have done this kind of automations in R. In R, also in Mathematica. Definitely much more in Mathematica than in R. So I would like to actually show something here. Let me see. This interface, what you see here, it's the Shiny interface implemented by RStudio, now known as POSIT. So they implemented Shiny in Python, but I have been using Shiny in R for quite a while, and so it's the same type of interface. What you see here, it's the same, more or less the same thing, much richer. But here, for example, I'm going to show how I'm going to find some point anomalies. For example, after I have made the fit, right? So here, let me actually put, so if I have this 0.5 or the median, right? So I have this curve which goes through these points. Now, if you look at the errors or the residuals, I can actually try to find which are the outliers just by using a certain threshold. I might say everything above 0.3 is an outlier, right? So something like that. And if I go here to this point anomalies, these are going to be marked. If I use certain, you can see this is with the threshold, and this is using the Hampel outlier. Outlier detector. If I use a different outlier detector, I might get somewhat different results. So another thing here, I don't want to overload this example too much. So let me actually do the last example with this interface. Let's do it at 90%. I'm doing something here which I thought it's going to show immediately what's going on. All right, so you can see how I have fitted the regression quantiles at 10% and 90%. So in a sense, I get the variance estimate for free. You can see that here I can actually find the anomalies according to variance. So not point anomalies, not contextual anomalies in the way I was talking before about outliers. Like like say here, right? These are my contextual anomalies. These are point anomalies. This is my contextual outliers. I'm saying that I actually can find the variance, right? So you can see this. I have marked the points in which the variance is too big. So basically, top outlier and bottom outlier variance is too narrow. All right. So I think we kind of went through this interactive interfaces section. It's in my to-do list to make this better, completely to implement in Python what we see here, which I have done in R. All right, so let me close these files here and go back to the presentation. So there's a big picture. I'm not sure how much I should talk about this, but we can say that there's in machine learning, there are basically four machine learning workflows. This is classification, regression, and latent semantic analysis. Somebody would put also recommendations. I do recommendation systems, and some people have successfully convinced me to include also a fifth part, which is the data wrangling. But data wrangling is not exactly machine learning, although closely related. And most of the time, most data scientists they do data acquisition, and data manipulation. So I've been interested to implement to have this monadic pipeline type of implementations for all of these workflows I mentioned, and the Python implementation of Quantile Regression was just missing. Again, somebody reviewed for me 4 or 5 years ago different Python packages for doing Quantile Regression. I wasn't that impressed. There's a certain certain efforts which I have put forward, so to speak, to generate machine learning workflows in different programming languages using natural language specifications. And so here, this is my next example. I'm going to show how this using large language models. So I'm basically saying, and that's an old implementation, which unfortunately haven't been updated. I'm not going to fight this. So this is really unfortunate. I wanted to show how this has been. This here it's completely wrong. So let me try to do some other. I think this is a very basically a certain classifier which is being used, and that classifier is classified. I'm going to run this again. I hope to get regression pipeline. So what is happening here? This is a natural language specification. I'm using a command. This is a command line function, right? Concretize command line up, if you will, in macOS. And so I have said that I want to get code in Python, and I'm saying make a quantile regression pipeline using 20 nodes. I dictated this, so it should be 20 nodes, But again, because large language models, they figure out this kind of misspellings, and the data set DF temperature. So we produce this pipeline. So I'm going to copy and paste. I think actually this is automatically put into the clipboard. Now there are a couple of mistakes here, and I'm not sure is this the large language models or it's the package itself which have put the probabilities in the in some additional parentheses. And so if I do that here, I need to actually DF temperature is data frame, and currently, so I need to basically take this two columns, absolute time and temperature, and this is what I'm doing here, right? This is what I have done here, and I converted them to NumPy. I didn't want the regressionizer package to depend on such a heavy package like pandas, and that's why basically at least at this point I'm saying, well, you convert it to NumPy, and it's going to guide you through, complain, if it cannot convert it. And so here we're basically this pipeline has been executed, and here we should be we should be getting the plots with the error plots. All right, so this was the application with large language models. So basically this was this other final element here, and it is related to the big picture because I want to have this kind of natural language specifications being translated to actionable codes. I want to have them for different machine learning workflows. And in general, if people have technological thinking, again, if my target audience is data scientists or data analysts, engineers, they should figure out from this code. It's much easier to change this code to do something less or more, and knowing what kind of after you have seen what exactly is the syntax. And so here, for example, I might just want to get this quantile regression plots, right, not the errors, and so forth, right? And here, with date plot has been put to false, but I can do it to be true, and I can say that I want my template to be this template which is for dark mode. I'm getting this in dark mode. So yeah, this is again for me it is a very good proof, so to speak, that from natural language specifications, I can actually produce correct and actionable programming code. So we're going here to questions and future plans, and I was talking about the big picture, probably a little bit too much. So in over the years, I've been asked different questions about quantile regression. So I'm going to kind of use some, let me see, can I open this here? Yeah, so this here is in some, okay, there's some advertisements, which unfortunately I think I muted it. And so now if we don't want to get, let me bring this up here. So this presentation, it has answered many questions. This is the 5th installment of this cycle of quantile regression lectures, and you can see I have answered some of the questions there. So multidimensional quantile regression, yes, it can be done. It is actually, I don't know, I didn't want to discuss this, but I guess I can do monadic quantile regression. And the monadic quantile regression, this is a Wolfram package, but I'm going to, oh no, this they should be the Packlet repository, and for some reason, again, like things are always a little bit different when presentations are being done. So let me actually look for monadic quantile regression, and I expect this to be here, right? So this is an official repository of Wolfram research, and so somewhere here I thought I had this multidimensional quantile regression, but let me go to another Parklet here, and maybe I'll find it. Okay, yeah, so here. So yeah, we can do multidimensional quantile regression. The thing is, can we plot it, right? And so, I mean, so you have, say, this data, and you can do, we can do fits like this, using this is the, it was just the median here. You can see at 10% and 90%, and I have some other examples with some other data. Hopefully, some of this is dynamic, some of this, I guess, not so dynamic. Different basis functions can be used, and there's some interesting question. So if the data is not filling in, it is very sparse, so it doesn't fill in all of the domain, what exactly happens. And so some of this here, it's showing that. So yes, it can be done. It's a little bit more careful, especially you need to be a little bit more careful when you do this in very high dimensions. So another question which happens relatively often, people who are familiar with the auto-recursive methods for finding models in time series. Let me actually show here. Yeah, I can use quantile regression instead of a RIMA, right? So this is what this Python notebook is discussing. Again, temperature data. I have fitted certain signal using some well-known basis of functions with infinite support, sine and cosine functions. Like, say, it's very similar to Fourier decomposition or Fourier analysis, Fourier transformation. But these basis functions were fitted through the data, and then if I have this fit, I can actually extend it, right? So in a sense, I have the model of the data. There's some multiple elements here. I'm not going to expand, but basically these coefficients which have been found for these basis functions, they tell me in a sense what is the model for this time series. So what happens if we fit through a few points? This actually happens often enough, right? People are kind of thinking, well, that's a tough question. Well, it's not that tough, and yes, it just works, right? It depends the packages, but by Roger Kionka, they're a little bit less stable for if you have too few points, because they're optimized for speed, and I'm using standard linear programming. So in a sense, my algorithm, although my algorithmic implementations both in Python and Mathematica, although they are slower, they can be robust in some relatively rare corner cases. And so the list of good features I already did in the beginning, but yes, it's a very good idea to list all of them and to have them in mind. What other anomaly detection methods can be used? For example, we can do anomaly detection using structural breaks. So do you use structural breaks? Do you find the structural breaks using quantile regression? Do you use linear regression? It's kind of an interesting question. We can use also different completely not based on time series and regression. They can be about time series, but they don't need to be. They can be based on recommender systems or nearest neighbors, so multidimensional type of similarity or dissimilarity of points. So again, this is beyond the scope of this presentation. So I think I covered all of the topics here, and this is it. Thank you for your attention.